A map of galaxies created using Australian telescopes under the leadership of Associate Professor Christopher Blake has produced new evidence that the expansion of the universe is accelerating and is driven by a smooth, diffuse dark energy that fills the universe and overwhelms the normal attractive force of gravity. Associate Professor Blake has helped to develop techniques to measure the properties of dark energy using the acoustic oscillations in the galaxy power spectrum as a standard ruler. These techniques are now commonly applied by cosmologists worldwide. Associate Professor Blake, congratulations. I invite you to present your talk on what is empty space, the physics of dark energy.
Thank you very much. I'd like to really thank the Academy for this honour and also acknowledge all my collaborators over the years, in particular Professor Warwick Couch, without whom I certainly wouldn't be standing here today. So I want to pose what might seem like a slightly unusual question to you today, which is, what is empty space? This might seem like a slightly odd way to spend taxpayers' money to investigate, but I want to hopefully convince you that there are some links to some very fundamental questions about the nature of reality. So we're in a slightly unusual place in the universe. I don't just mean Canberra, but we're sitting on a planet as part of a solar system in the outer suburbs of the Milky Way galaxy. But for those of you who read Douglas Adams as avidly as I did when I was a teenager will know that the universe is mostly a very vast and empty place. But in physics, there's no such thing as an empty space. If you put two uncharged metallic plates in a vacuum, those plates will feel a very slight attractive force beyond just gravity. And that happens because the vacuum is described by quantum theory. And in quantum theory, the vacuum is a teeming mass of energy and particles. So although this force may be a very small force in the laboratory, on the scale of the universe, it becomes a very important thing indeed. And so therefore it's of interest to researchers such as myself. So I'm a cosmologist, and the role of a cosmologist is to try and figure out what the universe is made of. And it may be an embarrassment to admit that that's such a simple question. We still don't have a very good idea of the answer. But on the other hand, it's a fantastic opportunity to really find out something fundamental about physics. But we actually have quite a good idea of the history of the universe. So cosmologists think the universe formed in a hot Big Bang, and the galaxies that we see around us today formed from the quantum ripples left over from the Big Bang. And I think it's quite a remarkable fact that we can understand what happened in the first few minutes or even seconds of the life of the universe. And that's because of the power of physics. The experiments we can do in the laboratory to reveal the physical laws are just as applicable in the first few seconds after the Big Bang. So after the Big Bang, the universe is expanding. All the galaxies we see are moving away from each other. But a very important discovery was made about 15 years ago, which is that expansion is in fact getting faster and faster. Now, this was, of course, the work of our Nobel laureate Brian Schmidt and his collaborators, who looked in particular at supernovae in the universe. And you can see an example here. Supernovae are particular forms of the deaths of a particular class of stars that go out with a bang. And the apparent brightness of supernovae in the universe tell you how far away those objects are. And when Brian and his collaborators looked at this, they found the supernovae were slightly fainter than they expected in a very distant universe. And so they were being flung away from us by this speeding up expansion. So in physics, every effect must have a cause. And so the cause of this speeding up expansion is called dark energy. So astronomers, when they don't understand something, like to call things dark. And this is another example. So dark energy acts as if the whole universe were full of little coiled springs which are uncoiling, releasing their energy and propelling this accelerating expansion. So my work is about trying to measure this mysterious dark energy in a new way, using maps of how galaxies are spread across space. So galaxies are the building blocks of the universe. There's probably about 10 billion galaxies or so in the observable universe. And you can see some pretty pictures of galaxies on the left of the picture there. But if you zoom out a bit, by a few 100 million light years, you find those galaxies are not just sprinkled randomly around the universe, but they're grouped into very distinctive patterns. On the right there you can see a representation of this where all the little dots are individual galaxies. So galaxies are a useful way for probing the universe for two reasons. Firstly, whether they like it or not, they're caught up in the overall expansion of space, and they allow us to therefore measure that expansion. But secondly, galaxies feel gravitational tugs from each other, which gives you a second way of using them to measure this gravitational force that we're interested in. And so the key thing we need to do to make such a map of these galaxies is to measure what's called their redshift, and this determines basically how far away they are. So this involves taking your galaxy and measuring its spectrum of light, so the rainbow of colours that the galaxy produces. And these spectra have a particular fingerprint which is based on the atoms that the galaxy contains. And so we measure that spectrum and we lay it side by side with a spectrum we might measure in our laboratory, and you see a shift. And that shift, or redshift, is driven by the expansion of the universe, which stretches the light as it travels from that galaxy to us. Now, one of the reasons I moved to Australia about 10 years ago to work on this research is that Australia is actually a world leader in this type of science, and that's thanks to the excellent national facilities we have at Siding Spring Observatory, which you can see here on the left side, a good day, and on the right side, a less good day when we were afflicted by one of these extreme climate events that Lisa was mentioning a moment ago. Luckily, I can say that our telescopes escaped unscathed, this experience of the Australian bush. So we've been using these national facilities to make our own galaxy maps, and I showed you a bit earlier this rich texture we had of the more local universe, a few 100 million light years. In this representation, that's just the middle pixel of this map, and the yellow swaths of points that you see emanating from here are the observations that we put together, which now go several billions of light years away from the Earth, in fact halfway back towards the Big Bang. And each of those little yellow dots is a galaxy whose position we measured. So I'm trying to think of a plot I could show from one of our papers that would try and convey to you some of the results we've got, and I settled on this one. So the y-axis that you can see on this plot is, if you like, the speed of expansion of the universe. And the x-axis is time going backwards, so you're looking out deeper and deeper into the universe many billions of years. And what you can see from our data is, in fact, the expansion of the universe undergoes this increase, this upturn. That's the direct physical signature of this mysterious dark energy. And so our results ended up being in beautiful agreement with Brian's supernovae measurements, and are confirming that about 3/4 of the energy of the universe is tied up in this mysterious dark energy. So now we want to know what this energy is. Now, if you look at the air in this room, a kind of cubic metre of hot air in front of me here, that's going to weigh about 1 kilogram. But if you ask how much dark energy is in the cubic metre in front of me here, it's more like 10 to the minus 26 kilograms, so not very much, about the mass of a proton, I guess. So now let's see if we can understand that with these quantum theory calculations that I mentioned at the start. So if you go and find your local friendly quantum physicist and get them to calculate how much dark energy we should find, they will actually get an answer 10 to the plus 96 kilograms. And so there's a bit of a discrepancy there. That's a discrepancy of 1 with 122 zeros after. So even when I was a student in physics, some of my mistakes were not quite as bad as that. So as usual in science, when you start trying to address a puzzle, you end up more confused than you were at the beginning. But this confusion actually gives rise to a whole set of new ideas, and I think that's why it's so important to support fundamental research, because you never quite know what you're going to find out. And so it's given rise to a whole set of different possible explanations for this dark energy, which are being pursued by myself and my collaborators, such as maybe we have to start from scratch and invent a whole new set of laws of gravity which might apply on the scales of the universe. Or maybe we have to fold up extra dimensions to add to the normal dimensions of space and time that we have in our everyday experience. Or maybe we have to stuff the universe with some exotic new materials whose existence that we didn't even dream of before. So it'll be very interesting to see what emerges over the next few years. We're currently actively trying to test some of these models using our data. And I think there's excellent prospects of Australia continuing to be one of the world leaders in this field, and that's thanks to some of our new investment in instrumentation, particularly the Square Kilometre Array, and this is an artist's impression, I should say. This is actually a radio telescope with lots of little dishes that's currently under construction in Western Australia and will be for some time to come. And this really promises to keep Australia at the forefront of this type of research, so I'm very excited about that. And so hopefully another speaker at your event in a few years' time can come back and tell you the final solution to this riddle of what is empty space. So I'll end there. Thank you very much.
Are there any questions or comments? Jerry.
Fascinating talk. I just wondered, is there understanding of why your galaxy map would have that very specific distribution, that particular profile?
Yes, good question. So that distribution you see is sculpted by the forces of gravity. Gravity is the most important force that acts on the universe as a whole. And so the gravitational pull that galaxies feel for their neighbours pulls them together in this tapestry of filaments and sheets and clusters. And we can use the mathematics of that pattern to really find out about, I guess, the force of gravity itself, which is what many researchers in the field are actively doing.
David Peake from Griffith University. If these observations had been made 60, 70 years ago, people wouldn't have been surprised. They would have just taken that as confirmation of Einstein's more general theory of gravity, which included the cosmological constant. No talk of dark energy then. Why has it changed now? Why do we talk about dark energy now instead of just the ordinary cosmological constant as a more generalised theory of gravity?
Yes, that's a very good question. Yes, so the cosmological constant has the properties of this quantum vacuum energy. And the main problem we have in this field is that if you calculate the amount of quantum vacuum energy, it's so discrepant from the amount that's observed by astronomers. And so that fundamental problem in our understanding of theoretical physics has given rise to all sorts of different explanations. So we now have this rich set of explanations which we really need to test with the data. And future projects such as this Square Kilometre Array will allow those tests to be made with great precision. For example, we'll be able to measure positions of all 10 billion galaxies in the universe and really start to use those to find out truly what is this dark energy.
Are there any further questions? Okay. Pippa? Sorry.
I'm Philippa Smith from the Office of the Chief Scientist. Great talk, Christopher, thank you. With the universe expanding, does that mean that there's a vacuum happening in the centre of the universe, or do you know what's going on in the very middle?
Yes, excellent question. So we think that the universe actually has no centre and no edge. That's a bit of a weird thing to say, I know, but our current data in fact says the universe is infinite in size. Now, the bit of the universe we can actually see is not infinite, because light travels at a finite speed and the universe has a set age. So the bit we can see is this sphere that's being cut out of this infinite universe. But any observer on a different galaxy or planet would see exactly the same type of physics that we see ourselves.
I know that many people want to still ask questions. In the interest of time, I think we'll close on this session, and then could you please join me to thank Mr. Blake?